Hello everyone, welcome to Sai Tutorials Jamkandi. In our tutorial, 10th class Kannada medium, English medium, 8th, 9th classes and also maths, science, English classes are available in the regular classes as well as online classes. So please join and learn the things. So dear students, in this today's session, let us learn about the physics second PUC chapter, that is third chapter, current, electricity. So in the previous session, I have discussed some concepts related to the conductivity, conductance, the relation between conductance, conductivity, electric field, and current density. And some concepts that is related to uh, limitations of Ohm's law. Just a second. And VI characteristics, how the graphs are going to vary, and effect of temperature on resistance. Okay, so these are all the previous concepts I have discussed in the previous session. Okay, so here thermistor concept, color code for resistors, it's not there for your syllabus actually, and it's also not there for your NEET examination, so and CET examination. So in I will discuss whatever the syllabus is there for you, that's enough for you. So other than that, if there in NEET examination, I'll definitely discuss. If not, I will not discuss. Okay, because it may make you clumsy about the concepts. So that's why I will discuss only the concepts which are related to your syllabus, and if it is not present in the syllabus, and but if it is there for the NEET examination or CET examination, I'll definitely discuss that concept. Okay, so these two concepts are not, I mean, color code for resistors, it's not there for your syllabus and also for your NEET examination, so I will not discuss it because it may make you confusion in the concepts. So that's why, see, dear students, in today's session, let us discuss further concepts, whatever there for your syllabus. So, we have learnt in the previous class, I mean previous classes, that is resistors in series combination as well as resistors in parallel. So, let us discuss what are the difference. Okay, what are the difference we can for. See, first thing is current is same through all the resistors. Okay, current is same. Current is same through all the resistors in case of series combination of resistors. But in case of resistors, voltage is same across each resistors. Okay. Okay. First thing is current is same through all the resistors, but here in case of parallel resistors, voltage is same. And second one, voltage is equal to the parallel, I mean series combination, that is V1 plus V2 plus V3 plus up to so on. But in case of parallel resistors, I is equal to I1 plus I2 plus I3, and also resistors. So the total resistors is equal to the parallel, I mean series combination of R1 plus R2 plus R3 plus up to so on. But in case of parallel combination, 1 by, I mean total resistance in case of parallel combination, that is 1 by Rp is equal to 1 by R1 plus 1 by R1 by R2 plus 1 by R3 plus up to so on. Okay. Now here here Rs is the greater than the greatest of all the individual resistance. Here Rs is the greatest. Okay, it is the greater than all the individual resistances. But in case of Rp, in case of parallel combination, is the smaller than the smallest of individual resistances. Okay, it is a smaller. Now, the applied voltage divides across the resistors according to the, see, the applied voltage, whatever the voltage is applied, divides across the resistors according to the ratio. It is in the form of ratio V1 plus V2 raised to V2 V1 raised to V2 raised to V3 is equal to R1 raised to R2 raised to R3. It is in the form of like this. Okay, and hence a series combination is a voltage divider. It is a voltage divider. The current divides through the resistors in the ratio I1 raised to I2 raised to I3. So this is the in parallel combination this will happen. So hence the parallel combination is a current divider. It is a current divider, that is I. Okay. In case of series combination, it is a voltage divider. In case of parallel combination, it is a current divider. How it will divide here? It is in the ratio of V1 raised to V2 raised to V3 is equal to the R1 raised to R2 raised to R3. So, and it is a in case of parallel combination, it is I1 raised to I2 raised to I3 is equal to the, what is the parallel combination of resistors? It is in the form of reciprocal of the individual resistors, that is 1 by R1 plus 1 by R1 raised to 1 by R2 raised to 1 by R3. This is the parallel combination. Okay. Sixth one. So if n identical resistors are there, okay, each resistance R are connected in a series, then their effective resistance is given by like this. So if you consider a n number of resistance, okay, if you consider n number of resistors in case of series combination, it is the Rs is equal to n into R. Okay, so for n identical resistors in series, this is this thing. Okay, therefore Rs divided by Rp is equal to, if you keep these equations in case of Rs and Rp, you will get n square. Okay, if n identical resistors of each of the resistance R are connected in parallel, then their effective resistance is given by 1 by Rp is equal to n divided by R. This is the effective resistance in case of parallel combination. So, when a series combination of, see, seventh one, see, when a series combination of resistors is connected to supply voltage, okay, when a series combination of resistors is connected to supply voltage, high resistance dissipates more power, that is P is equal to I square into R. Okay. See, when a series combination of resistors is connected to a supply voltage, okay, supply voltage, higher resistance dissipates more power. In series combination, which resistance have the high resistance, which resistance have the high resistance which will dissipates into more power, okay, more power. So that power is equal to I square into R. Okay. So is where I is the common current through the resistors. So if there are two resistors R1 and R2 in parallel, then their effective resistance Rp is equal to R1 into R2 divided by R1 plus R2. Okay, there if the two resistors R1 and R2 in parallel combination, then their effective resistance Rp is equal to R1 into R2 divided by R1 plus R2. When a parallel combination of resistors is connected to supply voltage, the lower the resistance dissipates a more power. Where that is which resistors in case of parallel combination, in case of parallel combination, which resistors, whether it may be this one, whether it may be this one, okay, which resistors having the low resistance, having the low resistance, which resistors having the low resistance, that will dissipate the power, that is P is equal to V square divided by R. Is it or not? So where V is the common potential across the resistors. Okay, see, in case of series combination of resistors, when connected in a series combination, where which resistors having the higher resistance, which resistors having the higher resistance, that will dissipate the power. But in case of parallel combination, which resistors having the lower resistance, that will dissipate the power, that is P is equal to V square by R. So these are the 6 differences we have learnt in combination of series as well as in combination of parallel resistors. Okay, I hope this concept is clear to you. Okay, now let us discuss the concept branch current. Okay, branch current. See, in case of branch current, what will happen? Uh, Number of resistance and a current will be produced inside the any type of conductor. Okay, current in one branch, in if you apply in one branch, it is equal to the main current, that is I, main current I, resistance in the branch, that is R. Okay, sum of the resistances, if you consider two resistances R1 and R2 in a combination, where combination of current is equal to the I. Okay, if you consider for I1, that is main current I, suppose it is R2, resistance R2, and the sum of combination of two resistors R1 plus R2. So if you consider current 2, that is I2 is equal to I into R1 divided by R1 plus R2. So this is the branch current formula, where current I is equal to the, suppose if you consider one current, it is the main current, that is obviously I, and the resistance in other branch, the if you apply the first current, I mean whatever the first current, the resistance will be applied to the second current, and there is a sum of the resistance of the two resistors. So this is the formula for the branched current. So here in this circuit, you will learn that this is the battery. Okay, this is the battery, the current flowing in this direction. Okay, these are the two resistors. These are the two resistors, and this is the key. Now cell or a battery, it is a cell or a battery. Now what do you mean by cell? Okay, what do you mean by cell? See, cell is an energy source. Okay, cell is an energy source used to drive charges and hence establish electric current in a circuit. So if I want to pass the electric current inside any material, I need to use current, that is I need to use current, that is I. See, an energy source, cell, an energy source used to drive charges and hence establish electric current in a circuit. So that is called as a cell. A combination of cells is called as a battery. Okay, so a combination of cells is called as a battery. Now, so you have got what is cell? Cell is an energy source. It is an energy source which is used to drive the charges and hence establish electric current in a circuit. So it is a what do you mean by battery then? A combination of these cells is called as a battery. Now, application of Ohm's law. Ohm's law Ohm's law applied to a, see, Ohm's law applied to a closed circuit. So suppose So let me derive an expression for this Ohm's law applied to a closed circuit. Okay, closed circuit. So consider a cell of EMF E. Now let us consider a cell. This is the battery and this is resistance and this is key. This is the main resistance R. Okay, which are connected to the EMF which are connected to the EMF E. This is the closed circuit. When it will be closed, we need to put the key on. Okay, it is a closed circuit. So when key is open, if no current is drawn from the cell. Okay, this is the cell. This is a small resistance, that is R. Okay. So consider a cell of EMF E and internal resistance, that is small r, connected to an external resistance, that is capital R, through a key as shown in the figure. Okay. So when key, that is key, this is key. When key is open, no current is drawn from the cell. Is it or not? So no current is drawn from the cell. So the voltmeter connected across the cell gives the value of EMF E. Okay. So whatever the EMF, it will give EMF value. Okay, where there is no current is drawn from the cell. Suppose when key is closed. Okay, when key is closed, current is drawn from the cell by the circuit. So current that is given by the circuit, that is potential difference across the R and potential difference across the small r, that is equal to I into R plus R. So current it will become I is equal to E. Okay, E divided by small r plus capital R, or capital R plus small r. We will get E is equal to I into capital R plus small r. Is it or not? Is it or not? Okay. Uh, So the terminal potential difference, we know that V is equal to IR. Is it or not? So if we substitute I value in case of current, so it will become E into R divided by capital R plus R. Also V is equal to, we can write here, this R get cancelled. V will become E minus IR. So this is the formula to find the current in the, volt potential difference across the two terminals of the cell. Okay. So this shows the terminal potential difference of the cell, which is less than the EMF of the cell. So this is all about the Ohm's law applied to a closed circuit. This is the Ohm's law applied to a closed circuit. So when a cell drives a current through a circuit, when it will drive the current through a circuit, when the key is when the key is closed, it will drive a current through a circuit. So work has to be done to drive the current through the external resistance and the internal resistance. External resistance, that is R, and internal resistance, that is small r. Then the current across the circuit, it will be given by E, electric field, E divided by combination of internal resistance as well as external resistance. So the terminal potential difference is V is equal to IR. If you substitute the equation, you will get the formula to find the Ohm's law applied to a closed circuit. So if you consider some kind of factors, state of cell in a circuit and terminal potential difference and current and resistance. So if you apply, if a state of a cell in a circuit is open, then potential difference V will become E, the current will become 0 and resistance will become infinity. Suppose it is closed, the electric flow will takes place inside the circuit. So that's why V potential difference will become E minus IR during the discharge, but V is equal to I plus IR during the charging. So I will become at finite and R is also finite. At a short, if you make the circuit short, then potential difference will become 0 and current will becomes infinity and R will becomes 0. So this is all about the Ohm's law applied to a closed circuit. Suppose grouping of cells. So let us discuss about the grouping of cells. This is very, very important. Suppose cells are grouped to get the necessary voltage and necessary current. See, this is the circuit for series combination of cells. This is the circuit for series combination. Cells in series. So, suppose this is C1, this is cell C1 and this is cell C2 and this is up to so on, this is Cn. Okay. So consider n identical cells such as C1, C2 and up to so on Cn, each of EMF E. Okay, each of EMF E. And the internal resistance, that is R, where R is a internal resistance connected in a series to an external resistance, that is to an external resistance. This is external resistance, that is capital R. Okay, is it or not? Since the cells are connected, since the cells are connected in series, so the total EMF of n cell will be equal to the E effective is equal to sum of the individual EMF, that is E plus E1, E plus E1 plus E2 plus E3 plus up to so on n into E. Okay, it is equal to n into E. Is it or not? Now, the internal resistance of the cells are connected in series, so that's why internal resistance, that is equal to the internal resistance, let me write R1 plus R2 plus R3 plus up to so on plus up to n terms, we will get n into small r. This is equation number 2 and this is equation number 1. Now, the effective internal resistance NR is in a series with the external resistance R. So, the total or equivalent resistance of the circuit, resistance of the circuit is equal to N plus NR. Okay, where this is equation number 3. See, the total effective internal resistance are connected to the external resistance. Therefore, it is equal to R plus NR. R plus NR. So now the current will become effective EMF NE divided by R plus NR, or this can also be written as I is equal to NE divided by R plus NR. This is the equation for current in a cells when connected in series combination. Okay, cells in a series combination. Suppose if you consider cells in parallel combination, just a second. Suppose if you consider cells in parallel combination, see this diagram will show the cells in parallel combination. Suppose this is cell C1, this is cell C2, up to so on. This is cell Cn. Okay. The internal resistance R1, R2, R3, up to so on, internal resistance Rn. Okay. Those are all connected to the external resistance, that is capital R. In the same way, consider the M identical. Okay, consider the M identical cells such as C1, C2, C3 up to so on Cm, each of EMF E and the internal resistance R are connected in parallel to an external resistance capital R, then the total EMF of the cell, that is E effective, is equal to E. This is equation number 1. In the same way, in the parallel combination, the effective resistance is equal to 1 by R1 plus 1 by R2 plus up to so on 1 by Rn. So this can also be written as equal to R divided by capital M. This is equation number 2. Okay. Now these are all connected. The internal resistance are connected to the external resistance. We will write it as R effective plus capital R. Is it or not? This is equation number 3. So if you substitute these three equation in the current, that is I is equal to total EMF E divided by total resistance. Total resistance, it is equal to R by M plus capital R. So this is the okay. This is the current, total current which is in the parallel combination. It is equal to I is equal to E divided by R by M plus R. This is the expression for cells in a parallel combination. Okay. Now let us learn about mixed grouping of cells. Okay, mixed grouping of cells. If you consider mixed, I mean number of, whether it may be in the series combination or whether it may be in the parallel combination, which will be in the mixed combination. So let M be the identical cells, each of EMF M. Suppose if you consider, so let me draw a diagram for a mixed grouping of cells. Suppose if you consider a mixed grouping of cells, that is m number of cells, EMF E and the internal resistance small r. So let these cells arranged in a m rows and each row contains n cells. So E effective will become, so the combination be connected across the resistance. Oh, now the E effective effective EMF is equal to NE and the total resistance is equal to the R effective is equal to NR divided by M. This is NR divided by M. So which are connected in a which are connected to the external resistance, it will become NR divided by M plus capital R. Now, so the total current in the EMF will be becomes, this is also equal to MNE. The total effective EMF divided by the total resistance, which can also be written like this. Okay. So the condition for maximum current in mixed grouping of cells is external resistance is equal to the effective internal resistance, that is capital R. Okay. MR divided by N. Now the maximum current given by the mixed grouping of cells, that is I maximum, is equal to MNE divided by 2 into root of MNRR, internal resistance as well as external resistance. So this is the expression for the mixed grouping of cells. Suppose external resistance which is greater than the internal resistance, effective resistance, the series grouping is preferred. Okay, so let's have the note here. When external resistance, okay, when external resistance capital R is greater than the internal resistance, the series combination is preferred. Suppose when that external resistance is less than the internal resistance, the parallel grouping is preferred. So to get more power, cells must be connected in a mixed grouping. To get the more power, the cells must be connected in a mixed grouping. So this is all about the note to remember. So now the maximum power transfer theorem, which is related to this parallel and series combination. Say whenever internal resistance is equal to the external resistance, the power transferred by a cell is maximum. Okay, this is called the maximum power transfer theorem. So what is this theorem statement it is. So whenever the internal resistance is equal to the external resistance, the power is transferred by a cell is maximum. This is called the maximum power transfer theorem. That is equal to P maximum I square into R, or where I is the E divided by R plus R whole square into R. So this is the power transfer formula. So in the next session, let us discuss about the further information related to your concept. So by this, I am going to wind up the session. Thank you.